Welcome to Tomorrow Unveiled. The last week in space, it felt different. Not just, oh cool, a discovery, but more like a real shift.
Yeah, I felt that too. It's like we're moving from tinkering with prototypes to actually deploying operational systems, things designed to last out there.
Exactly, building a sustained presence. And it feels like things are suddenly clicking together across different fields.
That's the key, isn't it? Physics, engineering, even policy changes, they're all starting to converge. It really does feel like the foundation for actually doing more in space permanently is being laid down right now.
And that's our mission for Tomorrow Unveiled today. We want to give you that shortcut, that synthesis of what matters. Our dedicated research team has pulled together the most corroborated breakthroughs.
We've sort of grouped them into three main areas, haven't we?
Yeah. First, the tech that gives us speed and strength. Think new engines and super tough materials.
Then the actual infrastructure going up, the orbital ecosystem, space weather monitoring, dealing with debris, commercial habitats.
And finally, this huge ongoing scientific puzzle, that interstellar visitor, 3IA lays. There's some really weird stuff going on there.
Oh, definitely. A proper head-scratcher.
Okay, let's dig in, starting with speed. GE Aerospace had these successful flight tests, supersonic, using solid-fueled ramjets, SFRJs.
Right. The ATLA's flight test vehicle. And the really interesting part is the engine tech itself. These SFRJs, they have essentially no moving parts.
No moving parts at hypersonic speeds. How does that even work?
Well, unlike a traditional rocket that has to carry all its fuel in its own oxidizer, usually heavy liquid oxygen.
Which adds tons of weight and complexity, right?
Mhm.
Turbo pumps, tanks.
Exactly. The SFRJ is an air-breathing engine. It scoops up oxygen from the atmosphere as it flies and uses that to burn its solid fuel.
Ah, okay, so it's carrying less weight because it's using the air.
Precisely. And that drastically increases its efficiency, its specific impulse, or ISP. We're talking potentially up to 1,000 seconds. That's maybe 4 times better than a typical solid rocket.
4 times, so that's a massive leap. Longer range, longer flight times.
For the same size vehicle, yes. And think about the simplicity you mentioned. No complex turbo pumps, fewer tanks, that solid fuel ramjet design.
Less to go wrong, especially at Mach 5+.
Absolutely. Simplicity often means better reliability, and reliability is key for scalability. Now, okay, the near-term focus is defense. Hypersonic weapons, that's the obvious first use.
The longer term.
Longer term, this kind of tech could make high-speed commercial travel, maybe even point-to-point cargo, much more affordable. Imagine crossing continents in, an hour or two? That could really change global logistics.
Okay, speed is one thing, but space is harsh. You also need strength, resilience, material science. Our research team highlighted 2 big developments here. First, this new cobalt-nickel-vanadium alloy.
Ah, yes. That one's interesting because of why it was developed.
Which is, alloys are developed all the time. What's special here?
The problem is most materials get incredibly brittle when they get super cold. They lose their strength, they can't handle stress.
Right, they just shatter.
Exactly. But this alloy, it was apparently engineered almost atom by atom. The goal was to keep both its strength and its ductility, its ability to deform without breaking even at cryogenic temperatures. We're talking down to minus 186 Celsius.
Minus 186. Okay, that's serious cold. That's like lunar nighttime cold or liquid oxygen storage cold.
All of the above. Think permanently shadowed craters on the moon, storing propellants for long Mars journeys. You absolutely need materials that can handle that without failing. It's fundamental for deep space hardware.
Makes sense. And you said there was a second materials win.
Yes, and it connects nicely. The European Space Agency, ESA, managed to 3D print a metal part on the International Space Station.
Metal? I thought they'd been 3D printing for ages up there.
They have, but mostly polymers, plastics. Printing metal reliably in microgravity is a whole different challenge. Different temperatures, different processes. This was a big milestone. It really paves the way for serious in-space manufacturing, or ISM.
Right, ISM. I've heard that term a lot. So the idea is manufacturing things in space, for use in space, like printing spare parts.
That's one half of it, yeah. The in-space for space market. Imagine needing a critical replacement part on a Mars mission, printing it on demand instead of waiting years for a resupply ship. Game changer.
Okay, that makes obvious sense. But you said one half?
The other half is in space for Earth. Manufacturing things in microgravity that are difficult or impossible to make perfectly down here because of gravity's influence.
Like what, for example?
High-value products. The classic example is Z-bland optical fiber. In microgravity, you can produce it with far fewer imperfections, leading to vastly better optical purity. Think next-gen communications, medical devices.
So you've got this dual strategy.
Mm.
Support space missions and make unique, high-value stuff to sell back on Earth.
Exactly. And that dual market is what analysts think could help overcome the second chasm.
Second chasm.
Yeah, the gap between proving a technology works in principle, like metal printing in space, and actually scaling it up into a reliable, affordable industrial process. ISM needs both those markets to justify the investment and build that industrial capacity.
Okay, that makes sense. So we've got faster engines, tougher materials, and a plan for making things in space. Let's broaden the view now to the whole orbital ecosystem. There was that really interesting launch, 3 space weather missions on 1 rocket.
Ah, yes, the cosmic carpool, as some called it. IMAP, SWFOL1, and CGO all launched together on a Falcon 9.
Why is launching them together so significant? I mean, besides saving on launch costs.
It signals a shift towards an integrated operational system. We've had space weather satellites before, but often launched piecemeal, maybe focused on research. This is about establishing the first dedicated 2057 operational monitoring network where the different parts work together, like a proper warning system.
Okay, so how do they work together? IMAP, that looks outwards, right?
Right. IMS sits out near the L1 Lagrange point and maps the boundary of the heliosphere where the solar wind meets interstellar space. Critically, it can give us maybe 30 minutes advance warning of incoming solar radiation storms.
30 minutes. That could be crucial for Artemis astronauts out near the moon, outside Earth's magnetic protection.
Absolutely vital. Then you have SWFOL1, also at L1. Its job is continuous operational forecasting of coronal mass ejections, or CMEs.
Those are the big solar blasts that can knock out power grids and satellites here on Earth.
Those are the ones. SWFOL1 is our main eye, watching for those heading our way. And then CGO, the third part of the triad, it orbits Earth and studies the geocorona, the outermost part of our atmosphere, to see how these solar events actually impact us directly.
So deep space warning, Earth-directed threat forecasting, and Earth impact monitoring. A complete chain.
It's the kind of robust infrastructure you need if you're serious about protecting assets in orbit and on the ground and sending humans farther out. It's planetary defense, really.
But speaking of protecting assets,
Yeah.
all this new activity, plus the existing satellites, Starlink, Kuiper, the debris problem isn't getting any smaller, is it? The research team mentioned over 40,000 tracked objects now.
Yeah, it's a huge concern. Kessler syndrome is the nightmare scenario, obviously. But even before that, just the operational complexity of avoiding collisions is immense.
So, what's being done? Any promising tech on the horizon?
Well, the research highlighted a couple of interesting approaches, moving beyond just nudging things slowly. First, there's a bidirectional plasma thruster concept from Tohoku University.
Plasma thruster. How does that work for debris? Do you attach it?
No, that's the clever part. It's contact-free. It fires a focused plasma beam to push the debris object gently. And because it's bidirectional, it can fire plasma both forwards and backwards to stabilize itself.
Ah, so it avoids that kickback problem, where pushing the debris sends your own expensive deorbiting satellite spinning.
Exactly. That kickback makes contact methods risky and complex. This plasma approach apparently tripled its effectiveness in recent vacuum tests because it's so stable and controllable.
Interesting. And the other one?
Transastra's idea, basically large inflatable capture bags. Think of it like a giant lightweight net you deploy to envelop debris.
Simpler than a robotic arm trying to grab a tumbling object, I guess.
Potentially much lower cost and more scalable, especially for capturing multiple smaller pieces or even larger defunct satellites. It's about finding practical, affordable solutions.
Okay, practical solutions. That brings us to the policy side. There was a big shift reported regarding the future of commercial space stations, right? The post-ISS plan. NASA's Commercial Low Earth Orbit Destinations, or CLD, program.
Yes, a major pivot. NASA moved away from the original plan of using firm fixed-price contracts for these stations.
Which means NASA basically sets the requirements and pays a fixed amount upon delivery. Lower risk for NASA, maybe?
In theory, yes. But the reality is building a private space station is incredibly expensive and technically challenging. We're talking billions up front, maybe $1 to $2 billion per year just to operate.
A staggering amount of private capital needed.
Exactly. And the firm fixed price model puts almost all that risk on the company. So NASA pivoted to using Space Act agreements or FTAs.
FTAs are more flexible, right? More like partnerships, sharing the risk and cost.
Correct. It's NASA acknowledging the huge economic hurdles and technical risks involved. They're essentially co-investing to help these companies get off the ground, recognizing that the market might not be mature enough yet to support purely private funding.
That sounds like a necessary move, but does it mean NASA is now underwriting potentially risky ventures? What if these stations don't find enough customers and fall into that financial valley of death?
That's the billion-dollar question, isn't it? NASA's trying to mitigate that. They didn't just hand out money with the SAAs, they added a really important new requirement.
Oh yeah, what's that?
The companies now must successfully host a 4-person, non-NASA crew for at least 30 continuous days. And get this, 25% of the SAA funding is withheld until they achieve that milestone.
Okay. So it's not just about building it. They have to prove it works and can actually support people for a significant duration, serving actual customers, before they get the final payout.
Precisely. It forces them to demonstrate operational capability and, crucially, likely forces them to raise significant private capital alongside the NASA funding to reach that point. It's a check, a way to ensure progress and real-world viability before the full government endorsement, if you like.
That CLD policy shift is really interesting. It's like NASA is trying to actively cultivate the market, but also putting guardrails in place.
Yeah.
A tricky balance. Okay, let's pause here for a moment. If you're finding this insightful and you're watching on YouTube, please do take a second to like this video, subscribe to Tomorrow Unveiled, and maybe even hit that new hype button. Apparently it helps us reach more viewers. And definitely turn on notifications so you don't miss future updates.
And if you're listening on a podcast service, maybe Apple Podcasts or Spotify, we would be incredibly grateful if you could leave Tomorrow Unveiled a rating and a quick review. It honestly makes a big difference in helping new listeners discover the show.
Absolutely. Okay, so we've covered propulsion, materials, orbital infrastructure, policy. Now let's shift gears completely and head out way beyond Earth orbit to this interstellar mystery. 3IA TLAS.
Ah, yes. The visitor from another star system. The analysis our research team looked at has turned up something genuinely bizarre about it. A real contradiction.
What's the contradiction?
Well, we know it's a comet, or comet-like, because it's outgassing. The James Webb Space Telescope observed it shedding material, losing something like 150 kilograms every second. Water vapor, CO2, typical comet stuff, mostly.
Okay, so it's active, like a little rocket engine firing off gas.
Exactly. And normally that outgassing pushes the comet slightly, causing what's called non-gravitational acceleration. It makes its path deviate just a tiny bit from what gravity alone would dictate. We see this with comets in our own solar system all the time.
Right, it's expected behavior, but not with 3ILS.
Apparently almost none. When the analysts crunched the numbers on its trajectory, using incredibly precise measurements, they found it sticking almost perfectly to the path dictated by the sun's gravity, despite blasting out 150 kilos of gas per second.
Wait, how is that possible? If it's firing off gas but not moving off course? What does that imply?
It implies the comet must be extraordinarily massive. Think about it. Firing a tiny rocket engine off the side of, say, an aircraft carrier. Is the carrier going to budge?
Not noticeably, no.
That's the analogy. For the observed outgassing to have such a negligible effect on its path, the nucleus, the solid body of 3I Atlas, must be huge. The research established a minimum mass, a minimum of around 33 billion tons.
33 billion tons. That translates to what, diameter-wise?
Minimum diameter of about 5 kilometers. That's a hefty comet. It's behaving as if it's a rocket engine. The outgassing is just way too small to significantly push the ship its massive nucleus.
Which is weird for a comet, right? Aren't they usually thought of as relatively porous, dirty snowballs, not super dense behemoths?
Generally, yes. This object seems structurally different, or at least far denser or more massive than typical solar system comets showing similar activity levels, and its composition adds to the mystery.
Oh. What's weird about its composition?
The data points to a really high ratio of carbon dioxide to water ice, something like 8:1 CO2 to H2O, much higher than most comets we're familiar with. And they also detected nickel in its plume. But without the corresponding iron you'd normally expect to see alongside nickel in solar system objects.
Huh. So different chemistry, different structure. Maybe.
It really highlights the scientific opportunity here, doesn't it? 3I Atlas isn't just a curiosity. It's a physical piece of another solar system, delivered right to our doorstep, relatively speaking. Its unique makeup gives us a direct measurement of the building blocks, the raw materials, from a completely different protoplanetary disk somewhere else in the galaxy.
A sample return mission without leaving home.
Kind of, yeah. It tells us that the conditions and materials available for planet formation might vary quite a lot out there.
And speaking of observations, our research team flagged something else, a kind of natural experiment about to happen.
That's right. Pure coincidence, but a lucky one for science. A coronal mass ejection, a CME, erupted from the sun, and calculations showed it was on a collision course with 3 IATLETs, expected to hit around September 25th, 2025. So very soon, actually.
So the sun is basically going to blast it.
In a manner of speaking, it gives scientists this amazing unplanned opportunity to use the CME like a natural probe. They can watch very closely how the comet's coma, its atmosphere, and its tail react when that wave of solar particles and magnetic fields washes over it.
What could that tell them?
It could reveal more about the structure of the coma, the composition, how tightly bound the nucleus material is. It provides real data to test against computer models of comets, especially one as apparently unusual as this one. Maybe it'll help explain why this massive thing seems so inert, despite the outgassing.
Okay, from an interstellar mystery, let's bring it back closer to home for our last section. The moon. Specifically, lunar logistics and how we're actually getting stuff there.
Right. The Commercial Lunar Payload Services Initiative, CLPS. This is NASA basically vying rides to the moon from commercial companies.
And the key update here involved Blue Origin.
Yes. They were awarded a significant CLPS contract worth up to $190 million to deliver a specific NASA rover called Viper to the moon's south pole, scheduled for late 2027.
Viper, Volatile's Investigating Polar Exploration Rover. That's the water ice hunting rover, isn't it?
That's the one. And this is the crucial point. Viper isn't just some small tech demo. It's a flagship NASA science mission. Its whole purpose is to prospect for water ice, to assess those lunar resources, which is absolutely fundamental for future long-term presence in situ resource utilization, or ISRU.
So NASA isn't just sending up small, low-stakes payloads via CLPS anymore. They're trusting a core strategic science asset to a commercial delivery service.
Exactly. It confirms that NASA sees CLPS not just as an experiment, but as the designated logistics backbone for supporting the Artemis program and the burgeoning lunar economy. NASA is fully embracing the role of customer, letting commercial industry handle the transport.
It really feels like a transition point, building the supply chain to the moon.
It absolutely is. It's fostering competition, driving down costs, and building that resilient capability needed to sustain activity on another world.
Okay, so let's try and tie all this together. We've covered hypersonic engines, super strong materials, space weather networks, debris solutions, commercial space stations, an interstellar enigma, and now lunar logistics. What's the big picture here?
I think the connecting thread this week is really about technological convergence and, maybe more importantly, the shift from possibility to practicality.
How so?
We're seeing multiple essential technologies maturing simultaneously. It's not just one breakthrough in isolation. It's the ramjets and the materials and the orbital infrastructure and the manufacturing techniques all moving forward.
And moving beyond just lab tests or single prototypes.
Precisely. We're seeing operational deployments like the space weather triad. We're seeing plans for industrial processes like in-space manufacturing. We're seeing the logistics chain being built like with CLPS. The focus is shifting.
Shifting from, can we make the tech work?
To, can we make it work reliably, affordably, and at scale? That's the second chasm we talked about with ISM. Can we actually industrialize these amazing capabilities? Do we have the manufacturing processes, the supply chains, the skilled workforce to mass produce and integrate these systems? That's the next big hurdle.
Mastering the production and operations.
Mm-hmm.
That feels like the defining challenge for the next decade in space.
I think so.
But we always love hearing what you think. If you're on YouTube or listening via your favorite podcast app, definitely leave us a comment. What are your thoughts on that interstellar mystery 3 IATLETs? Any theories?
Yeah, let us know. And maybe until next time, we can leave you with this final thought to chew on. We saw this week that the tech is maturing fast, and NASA is aggressively shifting risk to public-private partnerships, especially for things like commercial space station.
Right, the big SAA pivot.
So the question is, will the market for things like space tourism, microgravity research, in-space manufacturing, will that market develop quickly enough to sustain these expensive new commercial stations? Or is there a real risk of a financial valley of death where the stations get built, but the customers don't materialize fast enough to keep them viable?
Will the business case close before the funding runs out? That's a deep question for Tomorrow Unveiled. We'll have to see. See you next time.